Hi everyone, welcome back. This is our second videos on our thermal physics, and that will be the second half of our first lesson, and which is the heat and internal energy. Okay, so first of all, we need to go back to have a little bit review of what we've done in the kinetic theory of particles. Okay, so we've learned kinetic theory of particles. Okay, so in kinetic theories, there are actually two main points. One is no matter in what states, in all states of matters. Oh, sorry. Particles are moving. Oh, so that's what we need to know, the moving. Okay, and also we know that in all states of matter, particles exert forces on each other. So they are forces. Okay, they're forces. And we know that the kinds of motion and forces, they are common in all states of matter, but they behave quite differently. For example, in terms of the motion and particles in gas have the greatest freedom to move around, and also they move at the highest speed, okay, when compared to other two states. But in terms of the forces, we know the particles in the solid state, they experience and also they exert the forces at the highest magnitude, okay, and those forces could be attractive and repulsive as well. But when it comes to liquid and or especially gases, the forces only becomes very weak, and there's only attractive force among the particles. So that's why they behave differently. But anyway, we know there are forces and also they are moving, and so we think about the energy. So from the energy perspective, those motion and also the facts that they experience forces, that means, okay, so their energy related to this kind of movement. Also, there should be energy related to the forces between them, between the particles. Okay, and the energy related to the motion is called kinetic energy. So that means each particle in solid, liquid, or gas, they have kinetic energy. Okay, although these kinetic energies can be different, but they do have kinetic energy. And the energy related to the forces, or sometimes we use the word bonding, and they are called potential energy. Because all these kinetic energy and potential energy, they are at the molecular level. Okay, they are not used to describe the bulk energy of an object. Like they are not going to describe the kinetic energy of the whole body of a car, for example. So we give them another description. So this kinetic energy, we call them molecular kinetic energy. And also for potential energy, that's molecular potential energy. Okay, so in total, when the molecules, they have these two types of energy. They have molecular Ke and molecular Pe. So the sum of these two, when you add them up, they becomes the internal energy. The total of all the molecular energies and all the potential energies of the particles inside a body becomes the internal energy of that body. So that's how we relate all the concepts together. Okay. All right. Um, anyway. Okay. So is there any condition for the objects to have this kind of internal energy? Okay. Actually, there is, but you can say there's no, but theoretically there is such a condition, although that normally that won't happen. Okay, so that condition is a very extreme condition because it requires the object has a temperature as long as it's higher than the absolute zero. Okay, do you know absolute zero? So absolute zero temperature means minus 273 degrees Celsius. Okay, so no object in the universe can reach that temperature. So that's why this condition is something um, um, every objects will satisfy because all the objects in the universe has a temperature higher than that. That means all the objects in the universe will have uh, certain internal energy. Okay, right? So and for what I have said, internal energy of body consists of two components. There are two major components. The first is molecular kinetic energy. Okay, the other is molecular potential energy. Okay, what's the source? What it is related to? Molecular kinetic energy is related to the motion or the movement of the particles. The molecular potential energy is related to molecular forces. Another term you can use is the bonding force. That term possibly used more in chemistry. That's a bonding forces. We call there's a bonding between the molecules. So that's why there's certain degree of attraction, sometimes repulsion among themselves. Okay. Okay. So is there any factors that will affect the amount of internal body that a body can have? All right. So first of all, materials. Okay. So of course materials like certain matter they might contains more energy than more internal energy than others, but we don't need to discuss that as long as you know material is one of the factor. Okay, and we will discuss more like mass. So normally for a certain material, the greater the mass, the more internal energy one has. That's very sensible, right? Isn't it? Because the greater the mass, that means you must have more molecules in that object, and so that object will have more internal energy. Okay, and normally for a particular materials, higher the temperature, the more internal energy. For example, if you have a cup of water at um, um, 30 degrees Celsius and another cup have 50 degrees Celsius and the mass of the two cups of water are the same, then the one with 50 degrees Celsius will have higher temperature and more internal energy as well. Okay, so state of matter. So if you have the same material, same mass, okay, and okay, so for the state of matter, normally the one with the greatest internal energy should be okay, solid or liquid. So solid or gas. So we understand liquid is always in the middle of gas and solid. So what would be the states that will have highest or greatest internal energy given the same mass and same material normally? Okay, so is it solid? No, actually it's gas. Okay, how can we understand this? Just think about a simple phenomenon in our daily life. For example, you have ice. Okay, so you have 1 kilogram ice. Okay, And then from 1 kilogram ice to 1 kilogram water, what do we need to do? You need to heat up. You need to heat up. All right? So that means you need to supply energy for 1 kilogram ice to 1 kilogram water. Okay, and you will have 1 kilogram steam. Okay, if you heat up further. That means what? You supply energy for solid. Okay, ice is a solid, and that's liquid, and that's gas. So you need to supply energy for the solid becomes liquid, and for liquid becomes gas. Okay, so that means gas must have the greatest energy because they need to supply energy from solid to gas. Okay, so that's why we understand gas must have the greatest internal energy in it. Okay, that makes sense? Okay, so but you need to be careful when we compare two different objects. Like when you try to think about a kettle boiling water. So boiling water means 100 degree, and the iceberg, which is less than 0 degree. So obviously in terms of temperature, you would think iceberg has much lower temperature than the boiling water. So how about the internal energy in that bowl of water and the iceberg? Okay, so you might think boiling water must have the higher internal energy because what we've said here, temperature, higher temperature, more internal energy. But remember there are more than one factor. So there are other factors like mass. Okay, so even though you would say the temperature is much higher, but how about the molecules inside and the molecules here? Okay, of course, the iceberg will have, okay, tens or billions times of more molecules than those in boiling water, all right, in a bowl or a kettle of boiling water. So that's why even though the temperature is much higher, but mass is much smaller. Okay, so still you will say the internal energy in the iceberg is much greater than that internal energy in the kettle of water, right? Good. So don't just look at one factor. You need to combine all factors together. Okay. So for a particular object, how can we increase the internal energy? The first of all is of course the heating. That means you supply heat. You heat up. Okay. And so that's first way. And the other way is like hammering, bending. What do we mean? So if you are in winter time, you feel it's really cold, then you rub your hands together and you kind of feel certain you kind a bit warmer than before, right? So that means rubbing your hand could create the warmth. And also, and if you understand that whenever we we hammer something, we bend something many times, that object actually becoming heated up. Okay, so that means that's another way to increase the internal energy. We will call it doing work. Okay, so we will go back to that later. So doing work means you just applying forces to deform an object. You can do a little experiment by having a rubber band. You just stretch it like for 20 times and you could feel that rubber band becomes hotter. Okay, try this by yourself. It will only take you 1 minute to try. Okay, all good? Okay, then we are going to have a look at the temperature, the notion of temperature. We know temperature, okay, is something we could measure how hot an object is. But in terms of physics, what that degree of hotness, which is represented by temperature, means in physics. We understand the particles in a body are always in random motion. So that means they are keep moving all the time, and they move in random manner. You can't tell the direction of each particular object or particle. Sorry. Okay, so the idea is we find out that when temperature gets higher, actually the particles move faster. So that's intuitively true. It's self-evident. I don't think we need to elaborate that more, and vibrate more violently. Okay, so that means temperature has something to do with the speed of movement in those particles, which means they have greater kinetic energy. Okay, so that's why we relate to temperature with the average molecular Ke of temperature. Okay, so you can still think temperature as something, a measurement of the hotness of an object. But nowadays in physics, you can say temperature is a measure of the average molecular Ke in an object, which is much cooler way to say it. Okay, because only when you have learned physics, you know this kind of explanation. Okay, otherwise you can only say, okay, you measure how hot an object is. Okay, since the molecule move in a random manner, so that will come to mind again. So there is speed in a distribution. What do you mean by a distribution? Sorry, so you possibly haven't learned that before. Distribution means if you have something which have a range of values and range of different values, and you can just see how different speed or different kinetic energy will have a number of molecules, right? So you will see that these are the distribution curve. At 0 degree, okay, so the peak is around right here. So at the 0 degree, you see the peak is around a much lower kinetic energy, and when the temperature getting higher, that's the peak. There's a peak, and kinetic energy becomes greater again. So it just means, okay, so when we say temperature could measure the molecular Ke is not a very precise description. You must add the word average, because all molecules, they move randomly, so that means they might have different, they will have different kinetic energies. So your temperature is not going to measure all the molecular Kes for each particle. You can only measure the average outcome of all those molecules as a whole, right? So that's why I put the distribution here. You still need to remember, it's not just one speed or one kinetic energy. It's a lot of different kinetic energies, but they must have an average kinetic energies, and that average kinetic energies can be measured by using the notion of temperature. Oh, sorry about that. It's a lot of my keep talking. If you feel it's too much, you can pause the video, take a break. Okay, but I need to continue. There are lots of things to say. Okay, so another idea in the syllabus is about heat. Okay, so heat, there are two different meaning. Okay, in the classical physics, it's a process of transfer energy. Okay, another one is just the notion of thermal energy. Okay, so both can be used. You can use heat as a process of transfer energy, or you can use the notion of just one type of energy is called thermal energy. Okay. Okay, but anyway, so in our syllabus, it mentioned the thermal energy. It doesn't mention the process or transfer energy. Okay, so I might use the second definition more. Okay, here is the what's between two bodies in contact, and then when they say between them. Okay, so let's say here is just the energy. Possibly I would try to use I change my mind a little bit. Thermal energy transfer. So okay, that should be only two words, but I changed my mind a little bit. I try to use the exact wording in the syllabus. That's it. Okay, here's the thermal energy transfer between two bodies in contact when there's the condition for thermal energy can be transferred is when there's a temperature difference. Okay, so that means if you want to have thermal energy transfer between two different bodies, these two different bodies must have a temperature difference. They can't have the same temperature. If they have the same temperature, there won't be any heat flow. Okay. Okay, so that's why next heat must flow from the hotter body to the cooler. Okay, for example, if you have fire is around 1000 degree. Okay, so cold water is below 100 degree. So that's why the fire is much hotter than cold water. So you can use fire to heat up the cold water. Okay, so the result of that heat is you will see the low cold water becomes hot water. Okay, and because when you heat something, it increases internal energy. So remember, heating is one way to increase internal energy. The other way is doing work. Okay, heat transfer stops when the temperature of the bodies are the same. Okay, so if they are having the same temperature, then you can't transfer heat anymore. So that's why when you put your palms together, because the temperature on your left and your right hands should be about the same. So there won't be any heat transfer between the two. Okay. And also there's a rate of heat transfer between the bodies increases with temperature difference. Okay, so this is a bit abstract. What does it mean? So meaning when the temperature is higher, then that heat flow is getting faster. Okay, greater the temperature difference, faster the heat flow. Okay, for example, when you have a glass of hot water, okay, I just try to illustrate that. Okay, so like this is like 80 degree water, and outside is only 20 degree room temperature. Okay. Okay, so later on it becomes like, okay, decreased by 20 degree to say, okay, and the room temperature is still 20 degree. Okay. Okay, and then it becomes another 40 degree, another 20 degree less. Okay, so now it becomes another, so the room is still, so the room temperature won't be changed a lot when that water cools down. All right, so the problem is from 80 degree to 60 degree, you lost 20 degree. From 60 degree to 40 degree, you lost another 20 degree. But the problem is, will they take the same time? The answer is no, because the statements right here, the scientific fact is the rate of heat transfer increases with the temperature difference. So the greater the temperature difference, the faster the heat flow. So let's compare the temperature difference between these two. The temperature difference, so we use delta T to see a temperature difference, is 60 degrees. Okay, so the temperature difference here is only 40 degrees, and the temperature difference here is just 20 degrees. Okay, the greater the temperature difference, the faster the heat flow. That means you will take a shorter time from 80 to 60. Okay, so that might take you 2 minutes, but from 60 to 40 degrees, it will take you much longer time because the temperature difference has been decreased. So it might take you 5 minutes. Okay, I just randomly make up those numbers. Okay, just give you an idea. The heat flow will slow down when the temperature difference drops. Okay. Okay, so that's why when you see that temperature curve, so at the start, so this part is dropping fast, and this part dropping slow, and this part becomes steady, no dropping at all. So that's the idea I want to give you. Okay, and that's it. Okay, so there are a few examples about internal energy, heat, and thermal, and temperature. So we try to link up the few ideas. Internal energy, that means the total amount of Ke and Pe within the body of all molecules. Heat means the thermal energy transfer between two bodies when they have a temperature difference. And temperature is just a measure of the average kinetic energy within a body. Okay? So let's say which one's correct. The internal energy body is a measure of the total kinetic energy and potential energy of the molecules in the body. So total Ke and Pe, yes, that sounds correct to me. Okay, I just say take two bodies of the same temperature always have the same amount of internal energy. Okay, same temperature, two bodies, same temperature, does it mean same amount? When we didn't say whether the two bodies are with the same materials, whether they have the same mass. Okay, think about the example of a kettle of boiling water and iceberg. So, okay, so that means same temperature doesn't mean the same amount of internal energy. For example, if you have 100 degree boiling water and also of there 1 kilogram of this, and there's another 2 kilogram of boiling water, then of course 2 kilogram boiling water will have greater amount of internal energy, right? Here's a measure of energy transfer from one body to another as a result of temperature difference. It seems like textbook definition. If X has more internal energy than Y, heat must flow. Okay, so this one is quite interesting. It might take some time for you to think. You might pause the video, try to think about whether that's correct. More internal energy, heat must flow from X to Y. Okay, think about this. All right, you can pause the video. Yeah, try to look back for what we did before. There's something very close to it, but it's not exactly the same. Okay. Okay, if you've done your thinking, if you make your decision, okay, what's your answer then? Okay, my answer is wrong. Because more internal energy doesn't mean higher temperature, isn't it? Okay, it doesn't mean high temperature. Okay, I just give you one simple example. For example, if I have a cup of coffee, so coffee at like 60 degree, so it's quite hot. Okay, and then I'm going to have a, okay, that's iceberg. Okay, That's the one word, sorry, iceberg. Okay, so obviously you would say iceberg is like minus 4 degrees Celsius, let's say. And okay, so obviously that coffee has higher temperature, but since that's okay, that coffee is have very low mass, and this one is huge mass, like this is 1 tons, 2 tons, 2,000 kilogram. Okay, so that's only possibly 100 gram. Okay, so obviously you see that iceberg should have much greater internal energy. So in terms of internal energy, this one must have much greater internal energy because its mass is just much greater than a cup of coffee. But how about the heat flow? The heat flow, which direction is from the coffee to the iceberg? Why? Because it has higher temperature. Okay, so what determines the flow, the direction of heat flow is the temperature, not the amount of internal energy. Okay, so even though you might have much greater internal energy, that doesn't mean you have higher temperature. So just in this case, okay, think about this case and you will understand why. Okay. All right. So the next one is about okay, two metal boxes containing air standing in a room. Box X on the top of a heater. Box Y is on the bench. Okay, so heater and bench. Okay, both containing air. Okay, which line in the table best describe the average speed of the molecules? Okay, average speed of the molecule in the container. Okay, so I will give you some time to think about this one. All right, and then you make your decision. And also, okay, and we'll go back to see example 8. So just try to take your time to think about this for 2 minutes. You need to look back for some of the facts we stay there. Okay, so which is your answer? Okay, so we understand average speed of the molecule actually related to average kinetic energy, right? Average Ke. Okay, speed and Ke are not the same, but they are closely related. Higher the speed, the greater the Ke, right? The average Ke, but average Ke is related to what? Temperature. Okay, so obviously you will see the one above the heater should have higher temperature here. Higher temperature, that means. Okay, so that means the molecules in X should move faster than Y. Okay, but what are the options for Y? Is it 0 or slow? We know it will never be 0. They are always moving unless you reach the absolute 0 temperature, but that's impossible. Okay, so that will be my answer. Okay, so the last example is about water vaporize. Okay, vaporize, it just means liquid to gas under heating. Okay, so so why don't we use the word evaporation? Okay, evaporation means it also means liquid to gas, but it's not. But that's not under the heating. Liquid to gas under the heating is called vaporize, so it becomes vapors, it becomes gas. Okay, It's boiling point. Both water and steam are at 100 degrees Celsius. Both water and steam 100 Celsius. Compare the average kinetic molecules, Ke, molecular Ke and Pe in the water and steam. Okay, just think about the picture. Okay, so let's have a bowl right here. So you have heating up. Okay, so I'm having a lot of water bubble in it, and you will have steam. Okay, so let's say these are steam, and so steam 100 degrees steam. Okay, and okay, sorry, and here's 100 degree water. Okay, so you need to think about what's their average Ke. So which one has the highest, greater average Ke, and which one has the greater average potential energy. Okay, think about this. Take your time. Try to write your answer in words. Okay, how about 3 minutes? Okay, give you 3 minutes to think about this and try to write your answer out. Okay, pause the video. Okay, so here we are. All right, so I think some of you might think steam must have greater molecule Ke, because normally we'll say gas has greater moves moves at the higher speed than liquid and solid, right? That's generally true, but there's another more important concept. Okay, let's go back. Still remember this? So average molecular Ke depends on temperature. So that means if you have the same temperature, what does it mean? You should have the same molecular kinetic energy, right? So this one will override the much general comparison, like gas have higher Ke than liquid. Because gas have higher gas than liquid normally means because at a gas state, its temperature should be higher than the liquid. But when during boiling, both water and the steam, they are at the same temperature, 100 degrees Celsius, which is a very special case where the gas and liquid, they have the same temperature. All right, so that's the only case that the gas and liquid, they share the same amount of average molecular Ke. Okay, so let's say average Ke are the same for water and steam at 100 degree. Okay, because their temperature are the same, but here you only need to compare, so you don't need to give reasons. Okay, how about potential energy? Then obviously gas molecule, they are further apart, and the attraction between them is smaller, so the forces become smaller. So to have smaller forces, you must have supply more energy to separate them apart. So that means gas molecules should have greater potential energy. Okay, so the smaller the attractive force, that means more energy has been supplied to separate them, and that in turn meaning greater potential energy, right? So higher PE for the steam. So that's the answer. Okay, all good. Sorry for this. This I think my intention was like half and 1/2, but I don't want to separate this into 2 half lessons. So that's actually 1.5 lessons. So hopefully I don't stress you out for that. Okay. Anyway, okay. And the homework, you need to do the matching and some of the questions here. I'm not going to say how many questions you need to do. So you just, okay, my deal is always like if you have 1.5 lessons, so I try to keep each lessons like within the homework for each lesson is within half an hour for your homework and revision. So all you need to do is to spend 1.5 hour at most at the, okay, to do the homework. So if you spend more than that, just stop. You do other stuff. You study other subject unless you are really interested in my subject. I'm really pleased to know that. You just need to let me know. If you're really interested in physics like me, and that's a good thing. And you just try to do the matching and some of the questions here. It depends on how much time you can spend. So I'm going to put answers in OneNote later. Okay. I'm not going to say that you need to do 3 or 4 questions. Just do as many as you can, as long as you spend enough time. Okay. Oh, good. And so I think that's it. Okay. Bye. See you next lesson.